All right, let's start mathematical induction part one, proving formulas. So basically we're going to learn a new technique for proving formulas or equations type of situations. But I guess before we get to the example, let's talk about the definition or the principle. So let P of n be a property that is defined for integers n, and let a be a fixed integer. So basically a is just any number you choose. Traditionally we choose 1, but it doesn't matter. Suppose that the following two statements are true. So P of a is true, and then for every k greater than a, if P of k is true, then P of k plus 1 is true. So basically it's kind of like falling dominoes. You assume the first one is true, you assume k is true, so then, I'm sorry, you assume that it works for a fixed number, then you assume that it works for some general k, which means it should then work for k plus 1. So then you prove this piece by assuming this, okay? So then the statement for every integer n greater than a, greater than or equal to a, of P of n is true. So this is the technique or the method that we're going to use. So here are the steps on how to use this. Step 1, show that P of a is true. This is called the basic step. Just like I said, plug in like a number. I choose 1, whatever. Step 2, show that every integer k greater than a, assuming that this is true. So this is like your if part, and you're going to prove the then part, right? If then P of k plus 1 is true. This is called the inductive step. All right, so let's find an example. Here we go. So example, maybe we should do it on a different page. Yeah, let's make a different page. Just like this. Example 5.2.1. Sum of the first n integers. Use mathematical induction to prove that 1 plus 2 plus 3 all the way till n is equal to n times n plus 1 over 2 for every integer n such that n is greater than or equal to 1. Okay, so every integer that's above 1 or equal to 1, that this is going to be true. So step 1, right? Show that this works for some random number. Let's say 1, like I said earlier. P of 1 step. So is 1 equal to 1 plus 1 plus 1 over 2? Simplify this, right? This would be 1 equal to 2 over 2. So yes, first step works. So this is the method for proving something with induction. First you do this, then step 2. Suppose let's see, that's a good way to phrase this. 1 plus 2 plus 3 all the way to n is equal to n times n plus 1 over 2. Okay, so we're going to suppose this. We want to show that 1 plus 2 plus 3 plus n plus 1 more. Let me write it over here. 1 plus 2 plus 3 plus n plus 1 more is equal to n plus 1, right? I just add 1 more. Sorry, not on the screen there. So we're assuming this is true, right? That's what the inductive step does. Using this, we're going to try to prove that it is true plus 1 more term. So the next term, right? N plus 1. So that's n plus 1 is going to be n1 here. So that'll be n plus 1 over 2, which is the same as n plus 1 times n plus 2. So show that this is equal to this, right? So since there's a proof, 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2, then one moment. Then we will just add this piece here. See how this is just adding an extra part. So we're going to show that adding this is the same as adding it to the other side. So we're going to start with this and add it to then. So we're using this to prove that it is the same, right? So what is this going to be? This will be, add them together, that would be n times n plus 1 over 2 plus n plus 1. Repeat a common denominator, and that will give us n squared plus n, distribute that guy. Right, n times 1, distribute those two. 2n plus 2 all over 2. Here I just distribute, combine the fractions. I get this. Okay. So this will give us n squared plus 3n plus 2 over 2. And if you multiply this out, you will see that this is the same. Let me show them the last step over here. Conclusion, right? So therefore, n squared plus 3n plus 2 over 2 is equal to n plus 1 times n plus 2 over 2. All right, now let's go ahead and show that. So multiply that out, that'll be n squared plus n. Right. Oops. N squared plus 2n plus n plus 2, which is what we wanted to show. Okay, so that's the idea. We One more time, let's go through this and piece by piece. Right? We want to prove this formula here. Step one, plug in 1 and see if it works. Yeah, it's true. Cool. Then assume that it works for n. Assume that it's true here, and then you're going to try to prove that it's also true for n plus 1. So you want to prove that this is equal. So what we ended up doing is we start with this. So since we're assuming this is true, this is the part we suppose. So suppose this, add this to both sides, ends up being the same as that. Therefore, proven. I just forgot to fold this out earlier. That's all. All right, let's do another one. All right, so the formula we just proven can actually help us calculate sums from 1 to n. The only difference is they need to start at 1, so we may need to adjust or subtract the missing pieces, if that makes sense. So, but let me show you. So evaluate 2 plus 4 plus 6 all the way till 500. You see, that's the same thing as saying factor out of 2. That's the same as saying 1 plus 2 plus 3 all the way till 250, right? So we know we have the formula we just proved. We said 1 plus 2 plus 3 all the way till n is equal to n times n plus 1 over 2, right? So this can calculate sums for you. It just needs to be in this form. So n is 250 if I factor out the 2. So what I do is basically multiply both sides by 2, right, to get this one. So 2 plus 4 plus 6 plus all the way to the 500, right? That's our n. That's equal to 2 times this sum. But our n is 250. So that'll be 2 times 250 times 251 over 2. So this will calculate the sum. So the sum from 2 plus 4 plus 6 all the way to 500 is actually equal to 62,750 by applying the sum formula. Okay, let's do one more. Let's say we have to evaluate, right? Of course, we're not going to add every single one like crazy people. 5 plus 6 plus 7 plus 8 all the way till 50. So notice how it's not starting at 1. So what you can do is say, you know what, I want to start at 1 anyway. Right. Space, let me do it over here. This is equal to, right? If we pretend that this was included, right? You must then subtract that extra stuff we added. Okay, so subtract the stuff that's not supposed to be there. So now this is equal to the original, right? Subtract from this quantity. So if we were to use the formula, that would be equal to n times n plus 1 over 2 minus the missing pieces. where our n is 50, 50 plus 1 over 2, 1 plus 2 plus 3 plus 4, that's going to be what? 10, right? So minus 10. All right, so plug in our n is 50. N is always a stopping point. So that'll be 50 times 51 divided by 2 minus 10, that's 1265. So there's the sum. Okay, let's find another example here. All right, the next example, we're going to prove the sum of a geometric sequence. So for any real number r except the number 1, and any integer n greater than or equal to 0, the sum of r from 0 to n of r to some power is equal to this. So we're going to prove that this is true. We're using mathematical induction. Okay, so step 1, right? I can't use 1 like usual. So I'm going to show that. Well, first let's say let P of n equal this guy here. I gotta name it, right? Okay. So step 1, show that it works for some number. I'm going to choose 0 because it says 0 is equal to 0 or beyond is cool, just not 1. Choose small numbers because it's easier. So if I plug in 0, that means I'm going to get r. I plug it in here, right? So that would be r minus 1 over r minus 1. And if I plug it in there, you will see that that's the same. This would be equal to 1, right? If I plug it in there, you would see that r to the 0 is also 1. So yeah, we're good. It works for some number 0. Right? Remember the induction step, and it says it must work for some number a. All right. Now let's do the inductive process, or step, I should say. All right, so step 2. Suppose, right, we pretend that we know that this works. We suppose that this is good already. Which is weird. When we're trying to prove something, we don't usually suppose what we're trying to prove, but induction says, well, we suppose that the original works, and if we prove the next one works, then it works in general. So that means it was good to begin with, right? So it's kind of like you take the first domino and say, you know what, this first domino is cool, and push it over, and it knocks all of them down till infinity. So that means I'm good, right? So we're going to suppose this, all right? And we want to show we must show n plus 1 from I equals 0. I'm going to add one more. R to the I is equal to R to the n plus 1 minus 1. Oops, I should say n plus 1 plus 1, right? That was already there. So I'm adding 1 right there. Okay. Over R minus 1. Okay. So that would be equal to R to the n plus 2 minus 1 over R minus 1. So what we're going to do is we're going to start with, we're we're going to say, so we're supposing this, right? Hopefully I have no space here. So since this is equal to this, n plus 1 to the Ri is equal to, all right, now we're adding one more, so it's like we took the original and added one more term. Okay, so we're gonna work with this, right? So that would mean, so this, I'm gonna start over here. That is equal to R, where we said n plus 2. Oops, actually, sorry. That's where we want to end up. We're not going to start there. So I'm going to plug this one in, the original, which is right here. Okay, so we're going to end up with R to the n plus 1 minus 1 over R minus 1 plus R to the n plus 1, right? So you're substituting this guy right there. And that's right here. Okay, so now combine these. That will be the same as, so add the fractions, so it'll be Rn plus 1 minus 1 over R minus 1 plus R to the n plus 1, R minus 1 over R minus 1. So combine them, that'll give us, right, multiply that out, Rn plus 1 minus 1 plus, so R times that guy. Let me go ahead and show the steps. So I'm going to keep them separate for now. If I skip too many, then you'll miss it. So multiply those two, you get Rn plus 2 minus Rn plus 1. So all I did was distribute this into those two, right? Okay, so now combine them into one fraction. So that will be R to the n plus 1 minus 1 plus R to the n plus 2 minus R to the n plus 1. And notice how those are going to cancel, right? So these are gone once I have the fractions, which will give me R to the n plus 2 minus 1, which is what we wanted to show. Right? Let's see here. Yeah. So we showed that adding one more term is equal to this. So we must show this, and we did. Okay, so we did induction. So remember, just keep your head straight here. We first plug in a number, so make sure it works for one number, specific fixed number. I should say integer. Then we use this to prove that it works for the next one, n plus 1, just like we did the last example. Okay. So that's step 2, the induction step. All right, let's try applying the formula we just proved. So applying the formula for the sum for a geometric sequence. So this is a sum, well, honestly, I think that's a weird way to phrase it. A sum of a geometric sequence is the same as a geometric series, but anyway, it's whatever. So this right here is going to be like my R. Remember the formula says it's going to be, let's look at our formula, I already forgot. Here, right? The sum of some geometric, so notice how we have bunch of powers of 3, right? 3, 0, 3, 1, 3, 2, 3, 3. So 3 to whatever power is going to go here. And we apply the formula, and then we're going to get our solution. Okay, and that'll be our sum. All right. So that's all you have to do. Apply it in general. So what you need to recognize is that this is a geometric because it's just a bunch of powers of 3. They all have a common factor. 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is right there forever. Okay, so the solution is going to be 1 plus 3 squared plus 3 to the m minus 2 is equal to 3 to the m minus 2 plus 1 minus 1. All right, so I'm applying the formula to this r. So just plugged it in, basically. All right, so this will become 3 to the m minus 1 minus 1. 3, well, that's just 2. So let's go ahead and write it as a 2. Okay. Yeah, that's pretty much it. Sorry, I thought there was going to be more to it. Yeah, we're just applying the formula. You apply it in general, and this will be your sum. So summing this from 1 till forever to m is this. So this is a exact form versus a sequence of terms being added together. I don't think we need to do another one, but there is the sum. All right, so that's pretty much it for this homework, or for this section. So the homework will be basically messing with the induction, doing some basic formulas of sums, calculating the geometric sum, stuff like that. Basically stuff we just talked about. All right. Now let's start 5. The next section, chapter 5.